right, so this is the video for the Carnot Cycle for AP Physics, and what you will need to have in front of you is, I know it's a little blurry, I have it auto-focused on the screen, is from the packet, this picture right here so that you can see that part a little bit clearer, and then this chart, okay, because we're going to walk through that a little bit now, and this walking through the Carnot Cycle will also help you understand PV diagrams a little bit better as well, okay, before you do the before you do the multiple choice that correspond to this in the free response. Okay, so, all right, let me go ahead and hit restart. Okay, so here we have, new setup here. It's going to take me a minute to get comfortable again. Okay, all right. So here we have our gas right there. That's going to be our system. And then there's a piston, okay? And there's obvious connections here to some of the stuff we're doing with PV diagrams, and not just the Carnot cycle or Carnot engines, but in quotes, heat engines, or even internal combustion engine. You can use PV diagrams to help understand how those work as well, okay? But this is the one that's specific to the AP test, the Carnot cycle. All right, and so the gas is in there, the piston's there, and that piston can move forward and back, okay? And the gas that's in there can do work on the piston, or the piston can do work on the gas, okay? And we're gonna move around on this chart. So again, you should have the book out where you can take a look at the cycle as well. And we're gonna start, let's see, where do we start on this one? Whoops. Let me restart. Why does it keep I keep zooming accidentally. All right, so let's go ahead. We'll just start somewhere. Okay, so I'm going to go ahead. Let's go ahead and start at A. So we are starting at A up here. Okay, so look at your picture. We're starting up there at A, and we are going to go ahead and move to the right. Okay, now when we're moving to the right on one of these, I'm going to actually also just draw it here. So we're doing this. A to B. Okay, so when we are going from A to B, this is an isotherm. This is a spot where we have constant temperature, where the temperature stays the same. Now, how are we getting that to happen? This is actually that's just letting me know my tweets just went out. How do we get it to stay at the same temperature? Well, we have to interact with the surroundings, okay? Because if we're moving to the right, okay, if we're moving to the right, think about this equation for work, okay? We're moving to the right. Up here on the graph, we're moving to the right, which means our volume's getting bigger. So if I go ahead and start the simulation here over for a little bit, and then I'll pause, okay? You'll see that this piston is moving to the right, okay? So we are expanding. That gas is the volume's getting bigger and bigger and bigger, okay? So what about in terms of the work being done? Now this equation right here, notice there's no change in pressure here. I realize the pressure's changing there, but this equation can still get you the correct sign on work, okay? If we were actually going to calculate it, well, it's the area under the curve. We wouldn't have a constant pressure here. There'd be a little tiny bit of straightforward calculus, okay? But we don't have to do that for AP Physics 2. So even though the pressure's changing, it's still okay to use this equation to get the sign on the work, okay? All right, so we're moving to the right, so delta V will be positive. And we'll talk a little bit more about how this is possible in a minute to keep the same temperature, okay? But delta V is positive right there. Delta V is positive, okay? And now the pressure we don't have to worry about because we're not going to worry about the change in pressure, just the delta V is positive. So positive times a negative means my work done here will be negative. My work done is negative, okay? So work done is negative, which means there's work being done by the system, by the gas. The gas is pushing the piston to the right. If you want to think about it like that, that's fine. But there's work being done by the system, so that is negative work in this equation up here. Okay, I'm just going to put a little reminder that work done on is positive, work done by is negative. So there's a little reminder up there. Work done on the system, positive, work done by the system, negative. Okay. All right, so we got that as negative, okay, and this is an isotherm. How we get that to happen, we'll talk more about in a minute, okay, but the fact that it's an isotherm means our temperature stays the same. So let me go ahead and throw in another equation up here. U equals 3/2 NR, and our N's staying the same. N is the moles of the gas, or the number of gas molecules counted up, except expressed in moles, okay, so they're sealed in there, okay, they're stuck inside here. So the number of moles of the gas will stay the same. So U equals 3/2 NR delta T. Throw a delta U on there. Okay, so this is that U equals 3/2 NRT, or the one with the KB, and it's fine as well, okay, with this staying the same. So our delta T is 0. Well, if our delta T is 0, our delta U is 0. So I've got a 0 over here. So we've got, I'm actually going to put those below. Let me fix that up. So we've got work done is negative because we're moving to the right. Okay, our volume's getting bigger. Our delta U is 0 because our temperature is staying the same. And for an ideal gas where the moles are fixed, if delta T is 0, delta U is 0. Okay, there's no change in internal energy. Internal energy of this gas is staying the same. Okay, now just algebraically, if this is 0 and this is negative, Q has to be positive. Okay, so what does that mean? Okay, well, this is a really weird ideal scenario. Okay, so typically when we say Q is positive, that would be the surroundings are at a higher temperature than the object. Okay, and the molecules of the surroundings will bump into the molecules of the system. Okay, and as a result of all of those collisions, the molecules of the system will get going a little bit faster. Okay, that's that increased internal energy due to interacting with the surroundings. Now here's the part where this cycle is ideal. Okay, it's the best case scenario. So we have this gas in here, and then we have this reservoir around it. Okay, that can be various different things. And right now, it's at a really high temperature. So what's trying to happen here is this gas, as the piston moves to the right. Okay, I'll go ahead and advance a little bit more just so you guys can see that again. So let me go ahead and hit start, pause. There we go. All right, I'm going to go ahead and hit restart there for a sec. So as that piston moves to the right, I'm going to restart again. As that piston's moving to the right, you would expect the temperature of that gas to go down, okay? But it's not, okay? Why is it not? Because we've got this high temperature reservoir around it, okay? Now they have on there in their animation heats flowing into the hot gas, okay? But what's really happening here, okay, is that it's trying to cool off, okay, the gas that's in there, but the surroundings, that high temperature surroundings, those molecules here bump into these molecules here, bump into these molecules, which then bump into these, bump into these, bump into these. Except all of that, this is the ideal part. It's kind of like frictionless surfaces, a little tough to think about at first, okay? Or some of our other ideal scenarios. It happens instantaneously. So the molecules that are on the outside, normally this would take time, and you'd get a cooler center and a warmer surroundings. If this was a real engine in the real world, that would happen, okay? But this is the ideal scenario where we're saying, oh, instantly, the molecules that are here can bump into these, bump into these, bump into these, and as a result of that, they'll all stay at the same temperature. So we are absolutely interacting with our surroundings here, okay? And those surroundings are, in quotes, at a higher temperature, except because this is ideal, we're saying, okay, those collisions can all happen throughout the entire gas all in a split second. That's that perfect scenario. In the real world, it would take time for the molecules on the outside to bump into the molecules further in, further in, further in, okay? But this is the ideal part of it. Okay, so that's why our Q is positive. That's the weirdest part of this whole thing. Okay, we'll review that again when we get to the cool isotherm. Okay, all right, so that's our high temperature. So when we're up here, we're at some high temperature, and it is an isotherm. So if you look at your chart now from A to B, so in your packet, so from A to B, it's got delta T equals 0, okay, because it's an isotherm, temperature staying the same because of that hot reservoir around it, okay? If you want to picture the hot reservoir as a gas, a liquid, a solid, it doesn't matter because it's ideal. The collisions all happen instantaneously, okay? And we can also flip what's around it instantaneously. Again, not possible in the real world. Delta U is 0. We've talked about that, delta U being 0 because of this, no change in temperature, no change in U. Q has to be positive, okay? And there's two ways to get that. One, you could look at the work first, or you could say this is for a Carnot cycle. This is that high temperature reservoir, surroundings at higher temperatures, trying to cool off, that kind of thing. And I say they're at a higher temperature, not really because it instantly changes. And then W being, they have their negative QH, okay? Well, one of these is the negative of the other, right? If you just, look at the algebra there. So they have W equals negative QH, which is fine, okay? Because work should be negative, Q is positive, so that works out, okay? So that's our A to B, our isothermal expansion. Expansion because the gas is getting bigger, isothermal because the temperature is staying the same. All right, let's advance here a little bit now. Okay, so now we are going to go on the chart, from B to C. So I'm going to go ahead and add this over here. We're going from B to C. So on here, B to C. and this is going to be adiabatic expansion. So we're still going to be moving to the right, okay, on the graph, and with that piston moving to the right, meaning the gas is expanding. So we're going to have an expansion of the gas, and we're going from B to C. Now let me erase all of my stuff I have on here. Yes, some of it will stay the same, but I want to walk through it again. Okay, so we're moving to the right. So let's go ahead and since it's an adiabat, sorry, this is adiabat, or adiabatically. It's an adiabat. It's adiabatically. It's like adiabatic compression, adiabatic expansion. You could say it's expanding adiabatically. The actual line itself is called an adiabat. And when we have that, it means we're cut off from the surroundings. So our Q is going to be 0. Because remember, Q is all about molecules bumping into molecules. Molecules, of this case, of the gas inside that container, bumping into the surroundings. Well, now we have the best insulator, in quotes, perfect vacuum, okay, around this thing, okay? So that's why that's grayed out. It might be a little, the color balance might be a little off on there. The white balance might be a little off on there. But we have, just imagine there's nothing around this anymore. It's completely cut off from its surroundings, okay? So that means no interactions, no molecules bumping into molecules. So in that case, our Q will be 0. So I'm going to go ahead and put that up here. Our Q will be 0. And now we're still moving to the right. So if we're moving to the right, okay, in terms of on the graph, PV diagram, if you're moving to the right, your delta V will be positive. Keep meaning to put these underneath. Your delta V will be positive, so your work done will be negative. So I'm going to go ahead and put a negative in here, okay, for my work being done. And lo and behold, delta U should be negative, okay? So now we are to that scenario that I just talked about, whereas if this piston's moving to the right, okay, and there's that gas in there, and we're cut off from the surroundings, it'll do the thing that your intuition might tell you it do with an expanding gas that's cut off from its surroundings. The temperature is going to go down, okay? So I'm going to go ahead and put the delta U as negative, so my delta T should be negative, delta U negative, delta T negative, which means we're going to have a decrease in temperature. Let's go ahead and advance that. And here you can see, I don't know how well it's showing up on the camera, but this is supposed to be getting like a shade of bluish, okay? And that's what's going on. We're going down in temperature. So this is a change in temperature for sure. The first one, no. First one was an isotherm. This is an adiabat. Okay. Oh, and this another illustration of why you shouldn't start to think about Q as being tied always to temperature, because it's not. Okay, I realize in chemistry that when there was no work being done on anything, a lot of time that stuff lined up and worked well in your brain, but it's not that simple. Okay. All right. So we'll go ahead and again, U is the thing that you should start to get stuck in your brain is, oh, for ideal gases, if I'm talking about U, I'm kind of talking about temperature. Okay. All right. So we'll go ahead and keep advancing that a little bit more. All right, and now we're down here at point C. So let's take a look at the chart here in your PDF. So they had from B to C, the delta T is TC minus TH. So I'm going to go ahead and change this to match their notation. So there's the isotherm. That line is called an isotherm. The process is isothermal. Not that the language arts matters that much, okay? But there's that isotherm at that higher temperature, okay? And then now we're down here, we're going to be at some lower temperature at point C, or sorry, not at point C, they're just using T cold, which I will add on here in a minute for the cold reservoir, okay? So TC minus TH, they're just talking about what the actual value of delta T is. It's the temperature that we're going to have, the temperature we're going to have down here minus the temperature we had up there. That'll be our change in temperature, except I think, you know what? Our delta T should be negative. So that should be TC minus TH. Yep, that's right. They've done it correctly. Okay. Yep, final minus initial. That is correct. Okay, so TC minus TH will be our delta T. Our internal energy, okay? Well, our internal energy here is going to be delta U will be the same thing as W. So that's why they have written W2 there. So work done is negative, and since Q is 0, our delta U will be equal to W. For this particular setup, delta U is equal to W. Our Q is 0. Why? Because it's cut off from its surroundings, okay? You could also say because it's an adiabat, but it's better to think, oh, we're insulated from our surroundings, no interaction with the surroundings, Q has to be 0, okay? And then finally, last one, they've just solved with this equation and work, the 3/2 NR times delta T. For the work done. So if you can find delta U and W again are the same thing. So you could write W equals this. Okay, so that's what that That W equals for B to C, going from B to C. Okay. All right, so now we're down to C. Okay, let's go ahead and advance this a little bit more. All right, so now we're down here at point C, and we're going to start to do this. My picture is not good, okay? So you should, I'm going to go ahead and move my graph around here a little bit too. There we go. So this is pressure, volume. Okay, so this is going to be our cold reservoir temperature down here, and this will be another isotherm. So we're going to go ahead and have another isotherm down here. We're going to have isothermal compression in this case, okay, because we're going to start moving to the left. Look where the piston's at. We're all the way out to the right. So now we're going to start moving back to the left, okay? And this is going to be an isothermal process. So let's go ahead. Let me erase my signs up here. So get rid of that. Things are definitely changing. Okay, all right. And since we're isothermal, let's go ahead and start with the, that might be white. Let's go ahead and start with the delta T. So we know this is going to be a delta T of 0, so our delta U is going to be 0, okay? And if our delta U is 0 and we're moving to the left, let's get our sign on work, and then we'll talk about it more conceptually here in a minute. So I'm moving to the left, so my delta V will be negative because this piston's about to move to the left. So we're going to be squishing. Our volume is going to be going down. So remember, deltas, if something's getting smaller, our deltas are negative. If something's getting bigger, our deltas are positive. So we're moving to the left, okay? Delta V is getting smaller. This will be a negative. Negative times a negative means my work done will be a positive. So I'll go ahead and throw the positive in up here for the work being done. And now just algebraically, Q has to be negative, okay, for our first law of thermodynamics there to work out, which it has to, okay, for this object and its surroundings, okay? All right, so our Q is negative. Now, why is our Q negative? Okay, so typically when we're doing other types of problems, you just be like, oh, the surroundings are colder than the system or the object, okay? And then as a result of that, really I probably should say the gas. The surrounding, in this case, it's a gas inside the piston. If the surroundings are a lower temperature than the gas, then Q would be negative, okay? There'd be those molecules of the surroundings bumping the molecules of the gas, and the gas molecules, as a result of those collisions, would start to slow down, and the surroundings would start to speed up, okay? Now, that's not exactly what's happening here, because this is that instantaneous idea again. So these gas molecules will bump into the surroundings at that lower temperature, except those collisions, we're saying they don't take any time at all. They all happen instantly throughout the entire thing, okay? So as a result of that, if we can just snap our fingers and be like, okay, we're going to reach that equilibrium instantly. Every time it tries to change, we're just going to instantly get back to equilibrium in terms of temperature here. That means that our Q will have to be negative to make that happen, okay, because it's trying in quotes to warm up. I mean, your gut, probably most of your gut would be, if we've got a gas and we squish a piston, that the temperature would go through the roof, okay? But not if we've got this cold reservoir around it and we're allowing all the interactions with the surroundings to happen in no time at all. Okay? Again, this is that weird part. So let's go ahead and let it advance. There we go. You'll see the temperature staying the same. And that's our isotherm going from C to D. We're at that low temperature with the reservoir around it. Okay, whatever you want to picture, water, gas, solid, it doesn't matter because, again, it's happening instantly. Okay. And now we'll go ahead and go to, all right, now we're to point D. So now we're right here. Okay, again, you've got the good picture hopefully in front of you. We're at point D, and now, that wasn't in the way. All right, and now we're going to go from D to A. Okay, so going from D to A, we're going to have another adiabat. I don't have room to write adiabat, so I'm just going to put Q equals 0. It is in your packet there. So we're going to have another adiabat going from here to here. So we have flipped the switch, and now instead of having the cold reservoir on the outside of our gas in there, okay, we are going to have nothing. Okay, the world's best insulator, or a perfect vacuum, whatever you want to picture there. Like we took away all of the molecules. Okay, there's nothing around it anymore, so there's nothing to interact with. Okay, so if there's nothing to interact with, let's go ahead and put in here that Q equals 0. There's nothing to interact with. We're not going to have any molecules bumping into molecules, so no molecules of the gas in there bumping into their surroundings. If that can't occur, that has to be 0. Okay? And now let's go ahead and think about which way are we moving. We're moving to the left. Okay, we're squishing that gas, so we're moving to the left. And now, by the way, what you expected before is going to happen. If we're cut off from the surroundings and we're squishing the gas down, the temperature is going to go up. Okay, So we're going to have that delta V moving to the left is negative. Negative times a negative is a positive. So if this works out to be a positive, our delta U will be a positive. All right. If delta U is positive, just algebraically moving over here, and this is really what you have to do for a lot of the questions. It's just a bunch of signs on stuff when they're asking you conceptual questions, okay? To make sure you're thinking about it right, especially for an ideal scenario that's weird like this, okay? So delta U is positive, so therefore, again, n staying the same, so therefore delta T must be positive. Why did I write plus 1? Not plus 1. Delta T is just positive, all right, which means our temperature is going to go up, and we'll see that here. Again, I'm not sure how well the colors are coming out here, but it's going to go from a bluish to a reddish, so I'm going to go ahead and advance that. There's also a gauge over here for the temperature if the colors aren't quite working out, okay? So now we're all the way back to point A. We're at that high temperature. Let's take a look at our chart from D to A. Oh, I think I may have skipped one, okay? Let's go back to a moment for C to D for our isotherm. So for the isotherm that we had back here, okay, looking at C to D on the chart, the delta T was 0 because there's no change in temperature. Delta U was 0 because there's no change in temperature. For this is C to D, means no change in internal energy when we're talking about an ideal gas that has a fixed end, okay? QC is less than 0, so we had established that Q had to be negative for that to happen. That's when we had that cold reservoir around it, okay? And we instantly had all those collisions to keep the temperature at that same low value, okay? So it's as if the surroundings were at a lower temperature. It was trying to warm up. And then for work done, it was just that it was negative Q, okay, because we had to have that delta U of 0. So whatever we had for one, opposite for the other. All right, now let's go to D to A. So for D to A, going from D to A, we've got our, for delta T, temperature high minus temperature cold. So the hot reservoir temperature minus the cold reservoir temperature. So TH minus TC, that'll be our delta T, final minus initial. Our work done will be, they just have W4. Let's see here, our work done. Oh, instead of having an actual value there for the work done, you would have to, because we can't actually calculate it for this class. You have to have calculus to be able to do that. So for the work done, it's sufficient just to know that it is positive, that it is positive, and that delta U equals the work done. So delta U equals the work done, and they're positive. That's enough for us for this class, okay? And they don't have it solved anywhere anyway, okay? But you could. Actually, I just misspoke. We don't need calculus for that. Forget that, okay? So since delta U equals W, we have delta U because we have delta T. I apologize, okay? I was thinking area under a curve stuff. So delta U equals 3 off center delta T, so that's why they have the W4 there. So delta U equals the work done. Delta U equals the work done for that process. Q is 0 because, again, we have an adiabat here, so Q equals 0 for our adiabat. And then finally, for the work done, there's the actual equation. Our delta U and our work have to be the same thing. They have to be 3/2 NR delta T. Okay, that was your second, hopefully, pass at this. The first one, you had a little bit of a lecture yesterday, a little rough around the edges, but hopefully it was enough to make some sense of the reading. And then you were supposed to have already read that once. This should be take 2. If this is not take 2 for you, okay, you probably need to work through this more than once. Okay, we might have a take 3. We'll see how you guys do on the multiple choice and free response that correspond to this. Okay. Oh, I want to let it run through one more time here. So let it go through the whole process, just so you can see the piston doing its thing. And you really can, with temperature differences surrounding a gas, make a piston go back and forth like this. I'll probably put one in a playlist at some point. But Stirling engines, heat engines, there's lots of different variations on this. And yes, I said heat engines. But there we can see it going through. So cut it off from its surroundings, all of a sudden flush in some really cold water around it maybe, make the thing squish back down there. There we go, let it temperature go up, flush this, I can't keep up with this too fast. But you can adjust the play speed. Let me go ahead and do that. This simulation, that's too slow. This simulation does not work in a lot of modern browsers because of the Adobe Flash requirements and it being an outdated version of Flash. But I got it to work in Internet Explorer, so yay for old web browsers, I guess. I think that maybe that's Edge. I don't know. But there we go. Slowed it down a little bit. You don't actually have to worry about the numbers over here or anything like that. But if you have questions about this, like I said, keep that running list from yesterday, and we'll, after you've done the multiple choice and free response, if you haven't got the questions answered, you should absolutely let me know. There was an explosion of cars.